Okay, we'll go ahead and get started. I wanted to just touch base quickly with a few things from the web page, and also just so you can see how this is going to work as we go forward. The two things, the schedule's finally been updated a bit with the homework. Notice the later assignments may change slightly by a problem or two. The Mastering Physics assignment will always be the correct one, because that's the one that's getting graded. This, though, gives you an idea what it will most likely be and some of the upcoming due dates. There will be a few that may not be due on Sunday, just because once we start having the exams on Friday, it shifts the schedule slightly because of the way the lectures work. So just watch for that. But the first four will all be due Sunday at 11:30 p.m., and you can check that out. As the quizzes get available, the links will show up here for the quizzes. So that's a good page to keep in touch with. The information page is slowly getting filled in. You can see after today's lecture, the whole week, you'll have a separate thing for just the notes. That's the stuff I write. Okay? The PowerPoint slides pretty much just have, you know, the clicker questions and anything that was in the PowerPoint. And then you can go to the video, which is the full YouTube video. You can also use, I'll start putting in the podcast here, but you can get those directly from EEE. I do apologize. The first 2 days did not have sound. I think I've solved that problem. But it's the same sound that's on the YouTube video. So if you want the sound, just watch the YouTube video. Down here at the bottom are old exams. There'll be a few more that get posted as we get closer. These old exams are from an old enough version of the course that the order of topics wasn't exactly the same. So there's not like a one-to-one match between these exams and our exams, but the type of questions are the same. So you just have to look at them to see what fits. I will be posting last spring's exams, and those basically follow the same format. As I did, if you wanted to see what the problem was we'll be doing in class today, that already got posted, as well as the solution. I just want to check. Yep, the volume is going. Good. Now, what we did at the end of last class was this problem using a frame of reference. And I just kind of want to remind you of a few things as we go into today's class. Okay? The question, as you read physics problems, the key thing, which I will try and point out in lecture when I do the solutions, is what is the feature that tells you what type of problem it is. Okay? And you have to really read the question carefully. And you notice collide was in here. That's a key word we look for. We know we're doing something with a collision, and we'll have certain types of problems that have that. There'll be 2 or 3. This is one where you have things running at each other and you're finding the time. When you're finding anything about how long something takes, you realize almost always that's a kinematics problem. And I'll have to use something from that section in the course. So physics, it's what I call, a lot of students try and just do what is called plug and chug, where you just match your variables and your formula. That works for 25 to 30% of the problems in this class. So you could probably get a C doing that. What I like to describe physics as is advanced plug and chug. You have to start recognizing the key words, the key situations that tell you what type of problem it is. Because on the test, of course, it doesn't say problem from chapter 4. On the homework, it does. So that's something you have to do. The other thing is, so this was, you know, some versions of how I solved it. When I do it in class, my focus is usually on how you think about the problem, how you approach it, what you need to know to solve it. So it won't look like the 5-box solution because it's the first time you've gone through it. But I also will post for you, sometimes I'll do it that way. This one you'll have to blow up, it's a little hard to see. But I will also post for you what would it look like when you put it in the 5-box solution. So I did this one 3 ways, so there are 3 different versions of it that ended up getting posted. And you can see particularly how the strategy box comes out when I do it that way. So for every example we do in class, you'll get a version of the 5-box solution on the web to look at, because that's what you'll have to use on the exam. Make sense? Any questions on that? So what we're going to be doing now is really just building up our description of motion, starting with position displacement. And we're going to work in one dimension, we're going to work in two dimensions, we're going to build up the idea of vectors, and we're going to kind of integrate all this together, and we're going to start with constant velocity problems, move up to constant acceleration problems, and talk a little bit about general problems. So these are vectors. The key feature of the vector is the direction matters. We talk about position and displacement. Again, I'm just reviewing these quickly. They're in the book. The difference being, when I talk about position of an object, is always with respect to an origin. So if I'm giving you the position, I have to tell you where it's from, the origin, relative to where. The displacement is always a difference in two positions, or a change in position. And so here we have position A and position B, and the displacement right here is the difference between the two. And so whenever we have a change, we use the symbol delta. That means change. And whenever we have a vector, we put a little arrow on the top. So that quickly, brings those ideas together. And we're going to use those today. The other piece, and as you can see, this is why the notes get messy. Now, the other piece to this is distance, which is the total length traveled, and it is what we call a scalar, meaning it does not have a direction, it just has a magnitude. Now, the difference between distance and displacement is most obvious when I start turning. If I go in a completely straight line, there's going to be no difference between distance and displacement. But if I turn, this right here is my displacement between this point and this point. A and B, it's my position of B minus my position of A. This is my distance, the length of that curve. So you can see the distance is sometimes harder to measure because you're measuring along a curve. The distance is what your car odometer measures. That's something to keep in mind because it just measures how far you go. If you leave your house and you drive 2 miles away and you drive 2 miles back, your odometer will say you went 4 miles, but what's your displacement? 0. Why? You're back at the same place, so the same number minus the same number is 0. So that's a pretty standard problem to have to think about. Quick review of displacement, distance, position. Any question? So now, as I said in Wednesday's lecture, we get one less word. For velocity, we just deal with velocity and speed. Velocity is the vector with direction. Tells you where you're going and how fast. And we need to worry about the difference between average and instantaneous. And this is the difference between the displacement in some finite time and the derivative. And we're going to look at this in more detail, but I just wanted to gather in one place for you all the vocabulary we're going to be using. And what this means is if you're worried about average velocity or constant velocity, then life is simple. Your displacement is given by v times t, the time it takes. This is an example of a definition because we're just using that definition from up there. If you're not doing average or constant, otherwise, then your position as a function of time is the integral from t1 to the time you want of, well, let's call that t2, your position at t2 of v of t dt. And again, that comes from that definition. The inverse of a derivative is an integral. And so those are the two cases that we'll have. And then finally, we have acceleration, where we just have one word for it. Oh, actually, I should have said up here, when we do speed, we're just talking about the magnitude. And this is one of the more common mistakes people make in physics. They forget that we use a specific thing for velocity and speed. So you want to make note of that. Acceleration, again, we're going to do instantaneous, which is the derivative. And we're going to do average, which is just the change in velocity in some finite time. We're going to do average. And we have the exact same situation. The average acceleration, or if we have a constant acceleration, we will use change in velocity is a times t. And otherwise, whoops. Our velocity at some time is the integral from t1 to t2 of the acceleration dt. So those are the ideas we'll be using for the next 2 weeks. We're going to do a couple of today with frame of reference and constant velocity. We'll do next week where we work on a lot in one dimension with constant acceleration and velocity changing. And then the final week we do projectile motion, which is doing everything in 2 dimensions. And then that's what your first test will cover, is all of the motion stuff. Any questions on that? Excellent. So let's go to our first problem. So you're going to be chasing this bus, right? So you're here at the back of the bus. Here's the bus. You're already running. The bus is already driving. And you got to get to the front of the bus. Notice one thing. Really all you got to do is get to the door and jump in and hope it's open. But we already use an approximation that you're going exactly to the front of the bus and you're starting exactly at the back of the bus. Now, there's 2 problems in one here, whether you run at 4 meters per second or 8 meters per second. But the question is basically the same. Notice there's a first, are you able to get there? This is a yes-no question. And if you are, how long does it take? So we're looking for time. Now, this is an interesting thing that happens in lots of physics problems. You want to find time. So if you just started listing variables, the time is our unknown. I know the bus has a length of 15 meters. I know the bus is going 6 meters per second. I know me, the person, is going either 4 meters per second or 8 meters per second. Notice, I also have an equation. My equation is distance is velocity times time. What is an obvious mistake I will now make with this problem? I will plug in, look, I got V's, I got D's, I got T's, right? I'm done. And if I use these V's with these D's, you'll get it wrong. There's no combination of V's and D's on the board right now that will give you the right answer. And this is something that is very different about physics problems that does not show up in lots of the other classes you've had. There is unknown information that you need, that is not mentioned anywhere in the problem. So you have to figure out that there's something you need to find that's not even mentioned to be able to solve this problem. And that, 9 times out of 10, is what makes a physics problem hard. No matter what topic we're doing and how far we're going, what makes it complicated, and sometimes there's 2 or 3 of those. And that's what makes it even harder. So let's look at this one and how we might solve it. So what do we have? We have our bus. It's 15 meters long, and it's moving with some speed. And I have me right here, and I'm moving with some speed. And this is at t equals 0. You want to find, there is almost no physics problem that's a little bit complicated that doesn't become trivial or easier if you can draw the correct picture. I say it over and over and over, and people just try to avoid drawing pictures. I don't know why, but it helps you. What's our final situation? Well, the bus has moved somewhere, and I'm now at the front. This is what we want to have happen. And once I draw that, I can see the information I'm missing. The bus went some distance, and I went some distance. How many variables were missing? How much information was I lacking? This is an audience participation question, not rhetorical. Just because there's not a clicker doesn't mean you can't answer. How many pieces of information were missing? 2. Okay. Is there a relation between these 2? What is the relation? What does xp equal? Somebody shout it out. xb plus 15 meters. Now I'm going to start being careful because these are all vectors, and I'm going to make sure I tell you which direction is positive. You always need your coordinate system. Even if I'm in one dimension, the direction matters. So I'm going to make right positive. I'm going to use my little vector signs. What do I know about each of these? Well, I know xp equals vp times how long we're going. And I know xb equals vb times how long we're going. And now I count things up, and I'm actually done. I want to find t final. I have 3 things I don't know. I don't know t final. I don't know xp. I don't know xb. But I have 3 equations. So if I look at it, I have 3 things I don't know. xp, xb, and t final. But I have 1, 2, 3 equations. So I am done, and I can now solve the problem. That is where all of your effort is going to be, what we just did there. Once you have the point where you've reached the same number of equations and the same number of unknowns, the rest is algebra, and that I can't help you with. Okay? Well, we can. If you're having real trouble, come to office hours. But you got to practice that. You've got to seek help. That's not the physics. I will do algebra in class. I'll show it to you at different times. But most of the time, most of my effort is going to be focused on getting us here. I have a limited amount of time, and this is the hard part. I will always post the algebra for you. So first, any questions on how we got here? Excellent. Now I'm going to show you an easier way to do it. Right? And this has to do with frame of reference. If I work in the frame of the bus, right, then the velocity of the bus in its own frame relative to itself is 0. And all I've got to do is figure out, given the velocity of the person relative to the bus, I travel 15 meters because that's the length of the bus. Or actually, let's leave that as d. And I travel it in some time tf. And now I can just use right away d equals vt. All I need to know is this. I just have one other unknown. And depending how quick and comfortable you are with frame of references, you can figure that out either just using your intuition of which way they're moving relative to each other, or you can use our rule. We want the person relative to the bus. So our rule is that's the person relative to the road. That was given. That's the 4 meters per second or 8 meters per second, plus the velocity of the road relative to the bus. Right? Notice the r's have to cancel here. That was our other rule. But this one is just the opposite of the bus relative to the road, which is the other number we know, which is 6 meters per second. And so right away, we have two cases. Case 1, the velocity of the person relative to the bus is 4 meters per second minus 6 meters per second, which is a negative 2 meters per second. I've still taken to the right to be positive. Do I catch the bus? No, why not? Why? Not moving too slow. The bus isn't moving, so it doesn't matter how slowly I move as long as I do what? Yeah, I'm running backwards. Very hard to get to the front of the bus running this way. Very hard. It's a long distance, all the way around the earth. So very long time. And that's where vectors become key, right? This minus sign is the direction I am running. And I am running backwards. So the answer to case 2 is no. Did I have to solve 2 equations and 2 unknowns? Did I have to do anything fancy? No. I just got the answer right away. Did I have to recognize that this was a cool way to use frame of reference to solve the problem? No, I could have done it this nice long way. So you don't have to recognize it, but by looking for cues, this was 2 things moving relative to each other and asking ourselves when we're together. That gives us, oh, and they're both moving at constant velocity. So there's a frame of reference issue. Those are the key words we're looking for. And the constant velocity was a key one. Now for case 2, I'm going 8 meters per second minus my 6. I'm going plus 2 meters per second, so I can catch it. And the time is just the distance over the velocity, which is my 15 meters over my 2 meters per second, which is my 7.5 meters per second. No, it's not. It's 7 seconds. I don't know why. I did that when I was typing the solution too. Luckily, I caught myself there. Much easier on the algebra. And that's one of the slightly frustrating things about physics. You will find there's almost always 2 ways to do it. One way with more algebra and one way with less algebra. You'll still get the right answer. One last warning. And I'm going to leave it for you to do it, but if you use method 1 for case 1, you will solve for t final equals minus 7.5 seconds. What does that tell you?
You're probably wrong.
It tells you something very specific in this case. What does it tell you?
Go back 7.5 seconds, you'll be at the front of the bus.
If you go back 7.5 seconds in time, because of how you were running and the bus was going, you were probably at the front of the bus and it passed you, and that's why you're now at the back of the bus. Because you were running backwards. Right? Right? That's what we said. Case 1, remember, in the frame of the bus, is you're actually running this way. Which means to get here, at some point in the past, you were here, which is the front of the bus. Okay? What it tells you for this problem is you're running backwards. And so you can't catch the front of the bus. So notice, not only is there more algebra, but you have to understand more about your answer to get this one right. There are times where the negative answer is what you want. You want to know that, oh, they were equal with each other sometime in the past. And so it's a perfectly fine thing to have negative 7.5 seconds. It just, in the physical situation, most of the time, as someone said, it tells you something is wrong. In this case, not that you did anything wrong, just that you can't reach the front of the bus. Okay? We good with that? Any questions? Now, let's just emphasize one of the things that came out of this that's important for vectors. We say vectors have direction and magnitude. The easiest way to remember this, right, is you all remember the bad guy, right, in the movie, Despicable Me? Who saw the movie Despicable Me? Okay. And the bad guy, the real bad guy, not the good bad guy, his name is what? Vector, because he's a criminal with what? Both direction and magnitude, right? See, physics is everywhere. You have to pay attention. You will now all remember what a vector is. He's a bad guy. So let's look at it for displacement just real quickly. If we're in just one dimension, that means we can only move back and forth, right? We pick a positive direction. Say this is centimeters. And then we have our negative dimension. Now, if you start moving, where do I want to start? I want to start at point 2. I'm going to move up to 4 and turn around and stop here at minus 1. Now, the first question I might ask you is, what's the distance traveled? That's a scalar. What is it? Somebody do that quickly in their head. Careful. 7, right? Because you go 2 and then you do 2 again, right? 1, 2, 3, 4, 5, 6, 7. So you went 7 centimeters. You don't cancel out the little bit in the middle. It's every point that you travel. Now, the displacement, right? That's position vector A, which somehow I just erased. Okay? And then our final position is over here. So this is x1, that's x2. And our displacement vector is the final minus the initial. That's the definition of change. You want to keep that in mind. Change is always final minus initial. And our final is minus 1 because it has a direction. And then we minus our initial, which is 2 centimeters. So our displacement is minus 3 centimeters. And that is a vector. Now, remember we said we add vectors head to tail, right? And a minus sign flips one. So one way to look at this, right? Delta x is x2 plus the negative of x1. Well, x2 is that, and it's 1 centimeter long. That's its head. We take the tail. The negative of x1 is that, because it's pointing in the opposite direction. That's 2 centimeters. And the sum is the total length, and that's 3 centimeters. And they're all pointing left. And so that's why we know it's negative. So that's how you'll do it as a picture. This will become important next week with a lot of our constant acceleration problems in one direction. You really have to keep track of which way you're going. So let's go to our clicker question. Kind of late in the lecture. Took a long time to get it, but we're going to have like 4 really quick here at the end now. So the question is, which of the following is a vector? Negative 2% return on your investment, negative 5 degrees centigrade, minus 2 centimeter displacement, or all of the above. And let's see how we did. Interesting. Oh, good. There's 2 people who can't count. I guess I always give you the benefit of the doubt that E is none of the above, even though I don't write it up there. We got half the class going with all of the above, and the other half was something else. Interesting. Fight with your neighbor. Half of you are wrong. So try and figure out who's right. And then vote again as soon as you've decided. Wow. We're not doing very well at convincing our neighbor. Keep going. I didn't say stop. But it's like this. And now there's 6 people who don't know what they're doing. Yeah, you're just doing that to be obnoxious, I know. Now, I'm gonna say something here. Vectors have direction, and direction is given in one dimension by a minus sign, plus or minus. But does everything that have a negative sign have a direction? Just a thought. Might influence your vote. Ah, there it goes. 5, 4. Can you get in the right answer before I stop it? 3, 2, 1. And stop. Ah, almost. So C is the right answer. And the reason is very, very simple. There is a difference between a direction and a difference. Okay? So your return on your investment is really just a number. It doesn't really have a direction. It just has a magnitude. It just so happens that you can lose money. You might think of this as a direction, but it's really not. A vector really has to do with physically what it means. And this is just whether you're increasing or decreasing. And increasing or decreasing is just that. It's just a change, whether you're increasing or decreasing. Temperature of negative 5 degrees centigrade is just an accident that we put 0 where ice was frozen. Right? The real fundamental system of temperature starts at 0, absolute 0, and is Kelvin and goes from 0 to whatever, and doesn't have negative values. So temperature, this one's really clear. Temperature is just a scalar. It's just what it is. Displacement is definitely a vector. And we use the minus sign to indicate direction. It's a convention. But really, you could have just as easily used right and left as a convention, north and south, east and west. You know, how you label the direction is a convention. The minus sign isn't really intrinsic to that. It's the best mathematically because it allows us to do the arithmetic and the algebra easily. It allows us to work out that if I do 2 this way and 2 that way, we know it's got to cancel as a vector. Well, the easiest way to do that is use minus signs. So 2 minus 2 is 0. Okay. So there we go. There's the answer. Now, this one, I have to draw the graph for you first. or you can't answer it. So don't answer D yet, because there's clearly not enough information. We're switching a little bit our graph. Our other graphs were x and y. That was what we would call like a trajectory. We were drawing where it was moving in two-dimensional space. Now I'm going to plot for you x as a function of time. So you have to think about these a little bit differently. And I'm going to start with, whoops, no, I'm not going to start with a point there. I'm going to start, so this is 1, 2, 3. I'll start with a point at 2, 1, 0, and back up at 2. And this is the plot that they're doing. Okay, I missed the point. There you go. This is A, this is B, this is C, and that's D. And now you can answer which interval has the, which interval has the greatest magnitude of displacement? When I go from point A to point B to point, A to point C, or A to D? Which has the greatest magnitude of displacement? Let's see where we are. Excellent. Most people went with the correct answer in this one. 60% of you. Because this is where it gets tricky, and you have to pay attention to reading. Right? The displacement, right? Our definition of displacement is our position, that's our final position minus our initial one. And the magnitude of that is going to be the positive of that, the absolute value. Notice from A to B, we've got 1 minus 2. From A to C, we have 0 minus 2. This is negative 1, a magnitude of 1. This is negative 2, a magnitude of 2. From A to D, we again have 1 minus 2, which is just 1. So the greatest is A to C. Notice in this case, time is just telling us how long it's taking to get there. Right? It's not telling us about the displacement. The displacement is just final minus initial. And this is absolutely critical. Again, I can't say it enough in this first week. Take your definition, use your definition. Don't necessarily take your intuition. Don't take how the picture looks. Don't take what feels good. You know, take your definition, use your definition. Any questions on this one? Yes?
So the x represents the distance that you travel.
The x is your position at that time t. Yeah, which is a little different than the distance you traveled. That's actually an important question. Any other ones? Yes?
Why is A to D 1 minus 2?
A, because you stop at B and you started at A. You go from A to B. Notice, that's another excellent question. It's final minus initial. All of these start at A and finish somewhere else.
A to D.
Oh, A to D? Because D was at 1, wasn't it? Oh, sorry. Okay. Then it's 2 minus 2, which is 0. Good question. Which is still less than 2. I'm still right. I just can't draw straight lines in my head. Sorry, I thought you were saying B. Good question. By the way, I'd just like to point out that all I need is an 85% to get my A minus. So if I make a few mistakes in lecture, I'm still good. Say it again. In terms of displacement, yes, A to C, for magnitude of displacement, A to C and C to D will be the same. In terms, if the displacement is a vector, they'll be different, because C to D will be positive. If I look at that, if I want to ask C to D, I'm going to be doing 2 minus 0, which will be 2. So it'll be a positive displacement. But the magnitude will be the same. Now, the next important idea in all of this is just, I showed a graph. We want to now be able to go from those graphs, so let's make another one, to what the motion is actually like. So here's x of t, t. Now I'm not putting any numbers here, but these are negative and these are positive, and that's 0, and that's 0. This is just to give you an idea of what it would look like. So this is a common thing to want to graph, is x of t, and what we see is through this region, our position's clearly increasing. Right across here, it's constant. Here it's increasing. And here it's decreasing. So by plotting x of t, we get some nice information about the position. But one thing to keep in mind is if I was actually to plot x and ask what is it actually doing, right? At t equals 0, I'm here at some negative number, some negative position. I travel to some positive position at this point, and then I stop, and I hang out for a while, and I come back to 0. And that matches up there. And notice the two things give you two different information. The one down at the bottom really is very easy to look at and say, see your displacement. Because you can see where your final and your initial is. Right? Here's my final. And here's my initial. So there, right, I can get my displacement very easily from the picture. But notice it's hard to see that I stopped unless I write it on the curve. Here, it's easy to see that I stopped. I had a constant position. So that's one of the big differences between these two types of graphs. The other thing x of t is very useful for is helping us understand our instantaneous velocity. So let's suppose, I don't know, I had an x of t like that. Right? They're not straight lines anymore. And what you can see, here's my delta t, here's my delta x. So in this little interval, v average is my delta x over delta t. And then what do I want to do? I do calculus. I remember that the limit as delta t goes to 0 is now just v, and it's just that derivative. And the derivative is just the local slope. And so you can get a nice picture of what's happening by using the derivative and our calculus and doing instantaneous velocity. And we're going to do a little bit more with that. So that brings us to another key clicker question. This one we're just going to do kind of quickly. Why does a straight line in position versus time, notice we had a couple straight lines in that position versus time plot, represent constant velocity? Now, notice it doesn't change in time. It has 0 slope. It has a constant slope. Or my question could be wrong. It is only constant velocity when horizontal straight line. So real quickly, what this means here is in the plot like that, only this is constant velocity. That's what that's referring to. So doesn't change in time, has a 0 slope, has a constant slope. It is only constant velocity when it's horizontal and straight. And it is indeed c. Yeah. And this is one, notice, this is one that's kind of important. This, and this, we're all basically saying the same thing, right? Those are all position versus time being flat. Not changing in time, having 0 slope, being horizontal and straight. Position versus time That just means it's zero velocity, which is one example of being constant. This, a constant slope, position versus time, any straight line up, down, anything like that, is going to be constant velocity because the derivative will be constant, and the derivative of position versus time is velocity. So we'll close with that question. Next week we start in on acceleration.